Hello, this is the lecture corresponding to Chapter 3, Sections 3.4 and 3.5 of Basic Sentential Logic and Informal Fallacies, Phil 10 UCSD. The topic of this chapter is conditional proof. This shouldn't say second of two proof strategies. It should say first. Sorry about that. The second one we'll be getting in Chapter 4. I call it proof strategy because it's not a rule, it's not an inference rule, but it's another thing you can do in a proof to derive something. Now, I'll describe it, but then it'll make more sense when you start seeing some examples, and then you can come back to this description again to sort of solidify your understanding of it. The basic idea is you prove a conditional, you derive a conditional if phi then psi. How? Well, you assume phi and derive psi. Okay, that's the basic idea. In a little more detail. At some point in a proof, you decide you'd like to be able to derive the conditional if phi then psi on a line. Okay, whatever it is. Maybe it's the conclusion, maybe it's a conditional, and you know if you had that conditional, that would be a piece you need to get to the conclusion, whatever. But you identify this certain conditional you want. And you can't figure out how to derive it via the inference rules or replacement rules that we'll get in Chapter 4. Well, here's another way you can get a conditional, potentially. You add an assumption line consisting of the antecedent of the conditional you want. How did you derive that line? Well, you didn't derive it from any of the rules. We just assumed it. Okay, so it kind of came out of nowhere. But don't worry, because we're going to take care of the fact that we didn't derive this line. So you assume phi on a line, and then you just proceed using the rules. You keep deriving new lines. Your goal now, at this point, isn't to derive the conclusion of your proof. Your goal is to derive the consequent of the conditional you wanted, which is psi. Okay, remember you wanted the conditional if phi then psi. Psi is the consequent. You assume the antecedent. Now your goal is to derive the consequent. Now, suppose you can derive the consequent. Now at this point, we don't know if phi is actually true or if it actually follows from the premises because we just assumed it. We didn't derive it from anything. So we don't know if phi is true. We also don't know if psi is true or if it follows from the premises. Okay, yeah, we derived it, but we didn't derive it just from the premises. We derived it from the premises together with this line we just assumed. So we also don't know if psi is true. Okay? But what we have shown is that if phi were true, if phi were one of the premises, let's say, psi would be true. But this fact that we did demonstrate, if phi then psi, is just what the conditional means. That's what the conditional says, if phi then psi. So the subproof, this little thing we did where we made an assumption and then derived something else, demonstrates that that conclusion is true if the premises are true. Okay, let's see an example. By the way, after you see some examples, then you can come back and look at this explanation again, and maybe it'll make more sense if it didn't make sense this time. So here's an example. I've got a proof. I've got two premises. The conclusion is a conditional. So immediately on my radar is conditional proof as a possibility to derive this. Okay, so now I'm going to walk you through how to do conditional proof. Step 1. You get clear on what conditional it is you want to derive. Okay, now for me, I am clear. Right now, the conditional I want to derive is the conclusion, if G then K. So I know what the conditional is I want. Step 2. I assume the antecedent of that conditional. Okay, so I'm going to go ahead and do that. I'll show you how. What does it mean to assume the antecedent? Well, these are my premises. I'm going to write my new line, 3. It's going to be G, which is the antecedent. So justification is assumption for conditional proof, ACP. So I'm starting a conditional proof, subproof is what we will call it. It's a little proof inside a proof, so it's a subproof. And just to graphically show anyone looking at my proof that I've started a subproof, I'm drawing a little arrow here. So I'm going to indent. Okay. Now, I've assumed the antecedent. My goal now, step 3, is to derive the consequent of the conditional I want. Well, what's the conditional I want? Remember, it's if G then K, the consequent is K. So my goal now is to derive K. Okay, so now that's what I'm going to do. I'm just going to go back to using the inference rules, and my goal is to derive K. And you'll see that's going to be pretty easy. I have G, so I can get T by modus ponens on 1 and 3. Now that I have T, look at line 2. It's a conditional. The antecedent is T or S. Well, I have T, so I can get T or S by DI on line 4. Now I have the antecedent of the conditional on 2, so I can get K by modus ponens. Well, now I've achieved my goal, right? My sub-goal anyway, which was to derive K. Now what? Well, now what I'm going to do is I'm going to draw a line from K. This is where I'm going to end my subproof. I'm going to draw a little line from K all the way back up to that arrow of the original assumption. Okay, so when you've completed the conditional proof, subproof on the next line, so I've completed it now. I assume G, I derive K. On the next line, this is all you can do. You must write a conditional whose antecedent is the ACP and whose consequent is the last line of the subproof. Well, that's exactly what I wanted, right? I wanted a conditional whose antecedent was this and whose consequent is that. That's why I did the proof this way. That's why I assumed this and ended there. Okay, so in the next line, that's all I can write. And in fact, now I'm done because this is just the conclusion of the proof. Okay, so you see how this works. Basically, what I did is I made a little subproof in my proof. It's a conditional proof subproofs where I derived a conditional by assuming the antecedent and deriving the consequent. Okay, let's do another example. Here's another example where I'm going to use conditional proof to derive the conclusion directly. Now again, I need to emphasize, and we'll see some examples of this in a minute, it doesn't have to be the conclusion that you use conditional proof for. It could be something that you use to get to the conclusion. That's fine. But for now, I'm just going to use it to get the conclusion. What do? Well, the conditional I want is if x then y. What's the antecedent? X. So I assume x. Assumption for conditional proof. Now what? Now my goal is to derive the consequent of the conditional I want. Conditional I want is if x then y, right here. Consequent is y. So now my goal, my sub-goal in my subproof is to just get y. And you can see that's going to be pretty easy. I have x, so by modus ponens up here on 3 and 1, I can get not z. I have not z, negation of one of these disjuncts, so I can get the other disjunct by disjunctive syllogism on 2 and 4. Well, now I've derived the consequent of the conditional I want, so I'm going to close my subproof. The next line has to be a conditional whose antecedent is my ACP and whose consequent is the last line. Okay, so the antecedent is x, that was my ACP. Consequent is y, because y was the last line of my my subproof. Okay, let's see another example. Now this is going to be an example where the conditional I'm going to derive is not the conclusion. It's just something I need to get the conclusion. In particular, I'm looking at this and I'm saying, gosh, conclusion is M. How can I get M? Well, M shows up here if I could get this conditional, this is the antecedent, I could get M by modus ponens. How can I get if K then L? Well, it's not clear to me how I could get if K then L from this. So I'm going to use conditional proof. I'm going to assume K. Now my goal is to derive L. And you can see that's going to be pretty easy. I have K, so I can do modus ponens on 2 and 4 to get S or L. Now, line 3, not S, that's the negation of the first disjunct here. So I can get the other disjunct by disjunctive syllogism on 3 and 5. So there's L. It only took 2 lines. So I'm going to close my subproof. Next line is a conditional whose ACP is the first, whose ACP is the antecedent and whose last line is the consequent. If K then L. Now I can do modus ponens on 7 and 1. If K then L is the antecedent, I can get the consequent by modus ponens. Here's an example where I use conditional proof, but not to get the conclusion. I just used it to get a statement that I knew would be useful for me to then get the conclusion by using more rules. Okay? Let's see another example. Okay, this one is going to be interesting. Let's just run through it. I'm not going to sort of talk through it, but you can just see where I'm going with this. I'm going to assume R. And when I've assumed, and you'll see why. What's the condition I want? It's going to be if R then A. And you'll see why in a minute. Assume R. How can I get A? Well, now I can do modus ponens on 1 and 4 to get D and A, simplify A off. Now I can get the conditional if R then A. Okay. Right there. Now, what am I going to do? I'm going to do another conditional proof. So you can do more than one. So I'm going to start another subproof. I'm going to assume S. And my goal is to get if S then B. So I assumed S. How can I get B? Well, by 3/8 disjunctive syllogism. S is the negation of this first disjunct. I can get the other disjunct by DS. I'm going to close this subproof off. And now I've derived the conditional if S then B. By the way, my justification for these is always the entire subproof. Right, so when I derive line 7, it's 4 through 6 conditional proof. When I derive line 10, it's 8 through 9 conditional proof. So the justifications are always the entire subproof. Now, look, I've got 2 conditionals. On line 2, I have the disjunction of their antecedents, R or S. So I can infer by dilemma the disjunction of their consequence, A or B. And that's the conditional I wanted, is A or B. Okay, so basically, I'm just going to kind of highlight these. What I did is I used conditional proof to get me the 2 conditionals that I knew I could use with this disjunction and dilemma to get that. Okay, so this is another example where I'm using conditional proof to get pieces that I know I want. Okay. All right, so now that we've seen a number of examples of conditional proof, I want to step back a second and look at some rules, so to speak, for using conditional proof. So just to clarify, these are some things that people often do that they shouldn't do, and I just want to be explicit about how to do these things. Okay, so number 1, you always start your subproof by indenting and putting the little arrow, and your justification for that first line, your assumption is ACP, assumption for conditional proof. So that's how you start it. The conditional proof ends any time you want it to end. Okay? Now why do I say that? I say it because in chapter 4 we'll have another kind of subproof we can do, indirect proof, that requires a specific kind of statement. You can't end it any time you want. You have to have a specific sort of statement before you can end it. With conditional proof, you can end any time you want. What do I mean by that? Well, let's go back to our proof here. At this point, I assumed R, I managed to derive A, I ended it there to get if R then A. Okay. Now I could have ended it at line 5, right? And if I did end it at line 5, I would have had this conditional, if R then D and A. Okay, which would have been fine as far as conditional proof goes. I wouldn't have lost any points because I wouldn't have done conditional proof incorrectly. But this conditional doesn't help me. In fact, you can see I've already got that conditional up here, right? So it wouldn't have been wrong for me to do it, but it would have been pointless for me to do it. Whereas ending it where I actually did, waiting until I get A, that was useful because the conditional if R then A ended up being something that I could use well. So the point is you can end it anytime you want, but be strategic about when you want. Okay, you want to end it when you get the consequent of a conditional that's going to help you. Okay, number 3. When you're done, when you want to end it, when you've decided you want to end your subproof, you mark it off, you draw a little line from the end up to your original assumption. That's called closing the subproof. Also, it's sometimes called discharging the assumption. So you've sort of marked off or quarantined that little subproof. And you've done it graphically also with the lines. Next, number 4, the next line after you close a conditional proof subproof can only be one thing. Okay, once you close that subproof off, the next line has to be a conditional whose antecedent is your ACP and whose consequent is the last line of that subproof. Okay, now it's stated as a rule, but that's actually good. You want that because the whole point of doing a conditional proof subproof is that you wanted a conditional whose antecedent was the ACP and whose consequent was the last line. That's why you did it to begin with. Okay, number 5. All subproofs have to be closed before your proof can end. Okay, what do I mean? Well, let's go back to the proof I just finished. So when I got to line 6, this is what I had. I'd assumed R, I got D and A, and then I simplified A off. Now, you might think, oh, gosh, I've got A, I can just get A or B by disjunction introduction. Proof's over, yay. No, because if I had done this, I would have violated Rule 5. I'm trying to end a proof before I've closed all the subproofs. I haven't closed this subproof yet, so I can't do this. In fact, I should put a red X through that. Rule 6. Once a subproof has been closed, no individual lines in it can be used or cited anymore. Okay, once you close that subproof off, it's quarantined. You cannot cite any of those lines anymore. So what do I mean by that? Let's go back to the example I just did. I assumed R, I got A, got the conditional if R then A. Now I'm thinking, okay, how can I proceed with my proof? Oh gosh, I'm trying to derive if A or B. I've got A here, or I've got if D, then D and A here. So I'll simplify A off, and then I'll use that to get A or B. No, because notice here what I did is on line 8, I cited line 5, but 5 is inside a closed subproof. Actually, once I close the subproof 4 through 6, I can't cite or use any of these lines anymore. Okay, they're quarantined off. So I'm going to put a red X through that. This is the reason, by the way, this rule is why it's okay that I just threw an assumption here that I didn't derive. Remember, I didn't derive R. I don't know if R is true. I don't know if R follows from the premises, okay? Which means that anything I derive using R is suspect, okay? Because the rules are truth-preserving. If any lines I derive only from lines I already know to be true, I know are going to be true. Well, I don't know if R is true, so I don't know if D and A is true, and I don't know if A is true. Because all of these, this was an assumption, and these were derived in part on the basis of that assumption. So all of these things are suspect. So what I want to do is, before I continue with my proof, I want to close these off and quarantine them. These are the statements that I don't know about. They might be false. What I do know, though, is what my subproof demonstrated, is that this conditional is true. Okay, this does follow from the premises. So from now on, I can cite 7, but 4 through 6 are suspect. Okay, so that's the point of that rule. So I'm going to put a red X there. Cannot cite line 5. Okay, finally, section 3.5. This is something I've talked about a little bit, but I'm going to go ahead and make it explicit. Roughly, there's 2 approaches when you're doing a proof. Okay, and you can combine these 2 approaches in the same proof. One approach is just apply the rules. Wherever you see you can apply a rule and hope something good happens. What's a good kind of thing that can happen? You apply a rule, you derive a new line, and then something about that new line sparks a thought. Right? Like, oh, now I see. I can use this line with this other line and get the conclusion or something. The other possibility is to work backwards, and I've kind of done this a few times in some of the examples. But I want to sort of explicitly go through what it means to work backwards through a proof. What do I mean by that? Well, here's a proof, and I'm going to do this sort of by working backwards. I'm going to start at the end. I know that if this is a successful proof, the last line is going to be X. Okay, now I don't know how many lines it's going to be. Maybe this proof will take 2 steps, maybe it'll take 10. But whatever that number is, I'm just going to call it N. That's just some random number. Well, it's not random, it's the unknown number of lines in my proof. And I know it's going to be X. That's going to be the last line. And I think, how can I get X? What's going to be my next to last line? Or what are the rules I'm going to use to get X? Well, let's see. I see up here that I've got B or X. So if I could get not B, I could get X by disjunctive syllogism, right? So I'm thinking, look, if on the line, my second to last line, so this N minus 1, suppose my proof is 10 lines, N is 10, N minus 1 is 9. This would be line 9 and 10, maybe. If my second to last line is not B, then I could get X by disjunctive syllogism on 2 and 9, or 2 and N minus 1. So this will be my justification. Disjunctive syllogism on lines 2 and line N minus 1. Okay, well, how can I get not B? So maybe this is my second to last line. What's my third to last line going to be? My line up here. How can I get not B? Well, not B is here. If I could get R or C, I could get not B by modus ponens. Okay, so now I know if I can get this, I can do modus ponens here to get not B. So the way I'm going to get not B is by modus ponens on lines 3 and N minus 2. 3 and N minus 2. Well, now how can I possibly get R or C? Well, I've got R and P here. If I could bust R off by itself, then I could get R or C by the rule of DI. Okay, so I'm assuming that my line N minus 3 is going to be R, and then I'll be able to get R or C by using the rule of DI on line N minus 3 here. Well, now, notice, now I think, well, how can I get R? Right there, I can just simplify it off of line 1. Well, now I've sort of made contact with my premises, right? The line that I got here moving backwards is something that I can get from stuff that's already there. So now I've got my entire proof here. Okay, this is going to be line, so I've got 3, this is going to be 4, 5, 6, 7. So I know now n equals 7. So this is line 7, 6, 5, 4, and then I'm just going to put in the correct numbers for n minus 1, 2, 3. So I'm just going to rewrite this proof like that. So this is exactly the same thing I worked through, it's just now I know what n equals. N equals 7. So I filled in the correct numbers here. So this is an example of working backwards in a proof. Now in any given proof you can do a combination of the two. Right? I can work backwards for a while, but maybe you don't, maybe I didn't get all the way back. Maybe I only got to a certain point, and I got to a point where I realized, oh gosh, if I could get R or C, then I know what my last 3 steps would be, but I don't know how to get R or C. So then I just start applying rules. And then maybe how to get R pops into my head, or something like that. So you can use a combination of the two, but those are the two main approaches. Okay, that's it for this. That's the last lecture for Chapter 3.